Hi everyone, so this is the last lesson for chapter 9 of electricity in OCR. This is lesson 4, this is the last lesson. We're going to look at power and equations related to power, how to prove them, because you need to be able to derive them, and also how we calculate paying for electricity, which is a part of your adult life very soon. The energy transfer in circuits. We know that energy gets transferred always from a power source to any other electrical component. May that be a light bulb, may that be a resistor, may that be a diode or an LED or a thermistor. So we always have energy being transferred from the power source, whether that's a battery cell or a power supply. And it always gets transferred to other components through current. So current is what transfers the energy. So the rate of flow of electrons is what transfers the energy in a complete circuit. So we have energy from a battery, for example, being transferred to by current to another component. For example, if it was light bulb, it will be transferred in the form of heat and light. So that's a very clear and easy thing to know and also to describe. Now, what do we define electrical power as? You will see you will see power calculated in chapter 5, which we always define as the rate of energy transferred by each electrical component in terms of electrical power. When we say rate of energy, we mean per unit time. So every time we talk about the rate of something, we mean per unit time. So in other words, power is the energy transferred per unit time. Power is measured in watts. This is a derived unit, so we can get its SI units. We have energy, which we usually measure in joules, and we have time, which we always measure in seconds. So electrical power can be calculated using potential difference times current. So once again, the units are watts, potential difference is in volts, current is in amps. And the symbols are power, V, I. So very simple example, calculate the current drawn by a 12-watt charger, so we know that's power, when the PD is 5 volts. So I have this equation. I need to rearrange it for I, since I'm calculating I, so I'll divide both sides by V to get rid of V. V divided by V is 1. So current is power divided by potential difference. The units are all correct, so it will be 12 divided by 5, which gives 2.4 amps. So this is the simple form of the equation, how to use it. This equation can be derived from this equation. So power is V, I can be derived from the main definition of power in general. But we're using it, and we're using the derived form, which is easier when we're given power and current. But we will see a lot of derivations today, actually 2 or 3 of them, and you do need to know them all. So, other equations for calculating power, you will see that these are all given to you in the formula booklet, but you should be able to derive one from the other. So in order to do that, we need to use R is equal to V over I to show these 2 expressions first, and then I'll go on to how we derive the actual power equation to begin with. So I have 2 equations. P is equal to VI and R is equal to V over I. As you notice from, let me call this 1 and 2. So if you notice from equation 1, it only has I and R in the equation. So somehow, somewhere, we got V removed and R added. That means I will need to rewrite my expression in terms of V. So I'll multiply both sides by I, which gives me V is equal to IR. And I will substitute that in the original equation of electrical power, P is equal to VI. So I will just substitute it. V is equal to IR times I, which leaves us with I times I is I squared R. So this was a simple derivation, and so will be the second one. So if we look at so we've done the first one. If we look at the second one, the equation has V and R only, so it removed I somewhere. So we can use, again, R is equal to V over I, rearrange to make I the subject. So I will multiply both sides by I and divide both sides by R. I'll just do it quickly. So multiply both sides by I divided by I is 1. So I have IR is equal to V. So I will divide both sides by R now to get rid of R from next to I. That's 1. So I is equal to V over R. Now once again, I will substitute this in this equation. So I will substitute I in there. So power is equal to voltage times V over R, which is V squared over R. So I proved equation 1 and 2, how I derived them from using the other two equations at the top. Always remember, if one variable is connected to another, you can always substitute and rearrange. So the next part is what I would call a challenge, or it's not necessarily a big challenge, but we need to prove that P is V over I using this equation and the definitions for current and PD. So I'll do it here in the corner. So we know power is work done per unit time. Now the definition for current is the rate of charge flow. And we also know that potential difference is defined as work done per unit charge. A lot of you get mixed up that since V and I are mentioned in this equation, we should be using this equation. Well, we can't, because this is definition of resistance, not of potential difference or current. We want them to be based on the most basic quantities that they're defined with. So you can see already that I'm going to name them 1, 2, and 3. You can see that equation 3 has the same quantity as equation 1, so work done or energy transferred. So I will rearrange equation 3 to make work done the subject of the formula. To do that, we just multiply both sides by Q. So that will be V, so work done divided by Q times Q times Q. That's 1. So work done is equal to potential difference times charge. So now we'll substitute equation, I'm going to still call it 3 because we just rearranged equation 3. I will substitute 3 into 1. So that will be, so basically all I'm doing is I'm putting work done in there. So it will be power is potential difference times charge divided by time. But I can also see that from equation 2, Q is equal to, I is equal to Q over T. Q over T is here as well. So that means it's equal to I. So power, so this is equal to I. So power is equal to VI. To get full marks, you have to show it the way I did. Otherwise, you won't be getting full marks for a proof like this in an exam. If you don't show that you're linking I is equal to Q over T as an equation to this part here, then you won't be getting the marks because you need to make it very obvious. So that's how we arrive from power is work done per unit time or energy transfer per unit time to the equation that we are given and can use all the time. You might think, but why do we have so many equations linking power to something else? We do need different forms of equations that link different variables or quantities together. Sometimes you might be given current and resistance, and you need to calculate power. You don't need voltage, potential difference. Sometimes you might not need current, and sometimes you might need both. Depending on what the question gives you, then you have to figure it out. So we have another example here. It says to calculate the energy transferred when into heat, energy transferred into heat in 2 minutes. So time is 120 seconds. Gives you the resistance, and it gives you the current. Now you already know that power is I squared R, and you also know that power is work done per unit time. So you need to calculate the energy transferred, which is this part. But in order to get that, you need to calculate first the power and use the time. You can do it in two separate equations, so you could simply substitute the numbers here to get the power, which will be 2,880 watts. And since you need to calculate work done, that's power times time, which is equal to 2,880 times 120, which is 345,600 joules. However, the question gives us the lowest number. This is to two significant figures. This is to 3, and this is to 2. So the lowest number of significant figures is 2, which means I need to round my value to 350,000 joules. Another part I wanted to go through is to prove this equation, which is, I believe, also given to you. Let me quickly double check in the formula booklet. Yeah, that is also given to you. So since you see power is work done per unit time, so since you see this equation in chapter 5, you can find it in the formula booklet under the module 3 section. So power is equal to work done per unit time is found under module 3 section of the formula booklet, whereas the other equations we have just seen, so these 3 you can find under module 4 section of the formula booklet. Most of the equations are given to you. The only ones that we have seen so far from chapter 8 and 9 that were not given, and you should make sure you learn, are Q is equal to NE and R is equal to V over I. The rest that we have seen so far are all given to you. And obviously to remember laws as well. So Kirchhoff's first law, we're going to see Kirchhoff's second law next chapter, Ohm's law. These are the important things that you do need to remember for the course. Almost everything else is given to you. You should be able to derive some of them, and which I state as we go through the course. So we need to show that work done is VIT, which is also given to you, but you need to be able to prove it. We know that power is work done per unit time. We also know power is VI. If I rearrange the first equation to make work done the subject of the formula, so I times both sides by t, it will be power times time. And then I will substitute equation 2, so for power, into equation 1. That will be work done is IV. So I'm just substituting the IV part of power. VI times T. So that's how you get from that to that equation. These are the derivations and equations you need to know in terms of power, electrical power in a circuit that links current, potential difference, time, resistance, and so on together. So also from the definition of power in general, we said is the work done or energy transferred per unit time. So a more powerful device or machine, then it will transfer more energy per unit time than a less powerful machine. The same goes for people. If one person is more powerful than the other, then that means they can transfer energy from one form to another per second. So it can transfer more energy per second from one form to another compared to someone else. So the last part I wanted to mention here is the unit of power, which is the watt. Now, if a device has a power of 1 watt, that means it converts 1 joule of energy from one form to another in 1 second. So also the last thing I want to mention before I move on to paying for electricity is how we tend to use this equation to calculate energy losses per second. So energy wasted usually. So you'll usually find that this equation is the most helpful one because it includes how much current and resistance there is in a circuit, and hence how much is calculated or wasted as heat or in other forms that we're not interested in. Okay, so we can move. We looked at the equations and proved them. We also looked at the energy transferred. Now we're going to look at the very last part. Okay, so if you are not already aware of how your parents or your adults or grown-ups pay for electricity, all the electricity that is supplied to your home is measured by the electric meter. I would suggest that you have a look at it if you haven't looked at it before. It changes the amount of electricity that you use per day, but instead of doing it in terms of energy in joules, it does it in kilowatt hours. So the cost of the energy supplied to you depends on the power of the device and how long the device is used for. So if we go back to the equation of power is work done per unit time, you can see already that the energy transferred relies on the power and the time is used for. So I need to rearrange my equation to make energy transferred or work done the subject of the formula. I do that by multiplying both sides by t. T divided by t is 1, so it goes away. So work done is power times time. We already know this equation. We know the units that we need to use for these types of equations. So it's joules for energy transferred, watts for power, and seconds for time. However, when we use electricity at home, so for example, just turning the lights on for 4 hours requires about 8,640,000 900,000 joules in one day. So that's a huge amount of energy in terms of joules, even though 1 joule of energy is very little amount of energy, which also costs very little. So what they have done for home, to measure the electricity we use, because 1 joule is too little of energy. So like I said already, if you use the lights, I don't know, for 4 hours in one day, that will cost you, that will mean that you used 8, so for typical basically power rating light bulbs, that will come out to 800,640,000 joules. And that's just for lights in the house. So for example, if you use the kettle for half an hour in one day, it will be 3,960,000 joules. So that's a lot of joules to keep track of. So what they've done instead for paying electricity, they came up with the kilowatt hour unit. What this means is that instead of joules, so it's a derived unit. So instead of using power in watts, we express it in kilowatts, and time we express it in hours. So that leaves us with energy transferred in kilowatt hours. So let me do this once again on the side a little bit clearer. So work done is power times time. So the electricity bills, due to the huge amount of joules used, they instead use a derived unit called the kilowatt hour. Power is measured in kilowatts and time measured in hours. Obviously, you only need to use these units for really high amounts of energy being used for home, or if you're specifically asked to use it. Otherwise, you need to be sticking to the normal units. But for this topic, because we are interested in this, this is what we will be looking at. So, for example, if I have 1,500 watt hairdryer, so that's the power that's left on for 10 minutes, which is the time, how much energy does it use in joules and in kilowatt hours? So in terms of joules, it's going to be simply the 1,500 watts, but I need to change the minutes into seconds, so that's times 10 times 60. That will give us 900,000 joules as energy, which is quite high for something that we're measuring only for 10 minutes. And then if we measure this in watts, I need to change my power. So 1,500 watts is, if I divide that by 1,000 to get kilowatts, so that will be 1.5 kilowatts. So to get from watts to kilowatts, you simply divide by 1,000. And we need our time to be in hours, so we divide the minutes by 60, so that will leave us with 1/6 hours. And that is because 1 hour is 60 minutes. Then how many hours is 10 minutes equal to? This is a ratio question. Sometimes I use the method of 3. It's up to you how you prefer to do ratio questions. But just in case you're not used to it, just remember 1 hour, 60 minutes. How much is for 10 minutes in hours? You put a cross through. The two that have numbers, you multiply them. So that will be 1 times 10. And then the one with the question mark, you divide it by. So it will be 1/6. So yeah, let's do the calculation now. So work done is power times time, which is 1.5 kilowatts times 1/6 hours. So that leads to 0.25 kilowatt hour. So you already can see that if I was measuring in joules, so this is another unit of energy. Kilowatt hours is another unit of energy. So you can see that the joules, if I measured exactly the same thing, but you can see how this is a much bigger number in joules, whereas it's a much smaller number in kilowatt hours. So it's easier for electricity bills to arrive, especially since they take about 3 months to arrive, to build up. So let's define the kilowatt hour, and then we're going to have a look at how to calculate how much 1 kilowatt hour is in joules. So you need to know the definition. So kilowatt hour is defined as the energy transferred by a device with a power of 1 kilowatt operating for 1 hour. And you can see the 4. Remember what we said when we're multiplying values? We usually use the word for. When we divide it, we use the word per. It's a very important part in terms of helping you remember the definitions. So, if I wanted to know what 1 kilowatt hour is in joules, then I have to work through converting each unit from like kilowatts to watts and then hours into seconds. So let's do that quickly. 1 kilowatt is 1,000 watts times 1 hour, which is 60 minutes and 60 seconds. So that's 3,600 seconds. Leaves us with 3,600,000 joules. Hence why it's nicer for our electricity bills to arrive in this number rather than multiple numbers of this, which will look very messy and very, very big. So we already talked about seeing energy in terms of joules, which is the base, well, not the base unit, it's a derived unit too, but it's one of the basic units that are accepted in the equations, as long as we use watts and seconds to get it. We have also seen kilowatt hour, which is a unit of energy which we need to get by using kilowatts and hours as the units. And we will come, and this is for huge amounts of energy. And we have also seen electron volt, which we're going to look at more in depth, which is given in the format of this equation. So that's going to be coulombs and volts. In terms of what we get with the quantities that we use. But we will look at this later on more, so I'm not going to go into it too much. This is for tiny amounts of energy. And we'll go through it again. We have come across it briefly, but we will come across it again. Okay, so then how do we pay for it? So typical cost per kilowatt hour, which we call usually 1 unit of kilowatt hour, they cost between 6 to 15p per kilowatt hour. So for example, if I used 1 kilowatt hour, I might have to pay 6 pence for it. So if I used in a month, I don't know, 50 kilowatt hours, then how much do I have to pay? Then you just simply multiply 50 by 6. That gives you 300 pence, or pennies, whatever you call them, p per unit. What we have here is a power. So this is an example. How much does it cost to use an 800 watt microwave oven for 6 minutes? So we need to change that to kilowatts, sorry. You divide it by 1,000. In 6 minutes, you have to change it into hours. So you divide by 60. So 6 divided by 60 is 1/10 hours. And each unit costs 16.1p per unit. So the work done, or the energy transferred, is 0.8 kilowatts times 1/10 hours, which is 0.08 kilowatt hours. And if you want to know how much that will cost you, then that will be the amount you calculated. So 1 unit, well, whichever part of a unit, times 16.1 pence, which is about 1.2288 pence. This is per unit, so per kilowatt hour, so the units cancel, which means that the lowest amount of significant figures is 1, so you'll basically pay about 1 pence for using the microwave oven for 6 minutes. Okay, so this is the last part I wanted to show, regards adult bills, very soon to come to you as well. So what you usually get is the electricity used here. So it gives you the previous reading and the latest reading because it's just constantly accumulating over it. So when you take these two apart, you get the actual amount that you used between the specific time limit that you had to pay for it. If each unit costs 10.25p, then you have 480 times 10.25, and that will lead you to 4,920 pence, which is 49.20 pounds. So if you've done the calculation, it'll come up to that much. Obviously, you divide that by 100 to get it in pounds. It's 49.20 pounds. So yeah, this is the unit price for 1 unit, the amount that you use in kilowatt hours. So these are kilowatt hours, not in joules, because it's much easier. Now imagine multiplying these numbers by 3,600,000. That will give you a very long reading and makes it hard for people to understand. Okay, so we have finished chapter 9 officially now. We have looked at all the equations, and we also talked about the kilowatt hours, a unit of energy, and how to calculate the cost of energy. If you have any questions, please let me know.